Hello everyone. In this video we are going to study about the wireless and cellular communication, the CDMA topic. In the previous videos we have studied about the evolution of CDMA, its network architecture, and also we studied about the nodes, interface nodes and all. In this video we are going to study about the CDMA channel concept. So, before going into the channel concept, let us study how the generation of the channels are going to be done. In this CDMA 2000 cellular systems, that is the code division multiple access technology, is going to provide an additional user capacity over a limited amount of radio frequency spectrum. To enable these distinct but same frequency channels, orthogonal Walsh spreading codes are used for channel encoding. Several of these encoded channels are used specifically within the CDMA system. This is which is used to provide precise system timing, control, and overhead information, while other channels are used to carry user traffic. These Walsh codes not only describe the structure of the 64-bit codes and their usage of the IS-95 CDMA system. Each Walsh code consists of a binary combination of 64 zeros and ones, which is shown here, and all the codes except one who have an equal number of zeros and ones suffice to say to the 64 Walsh code used in the IS-95 CDMA systems have the unique quality of being orthogonal to one another. All other Walsh encoded signals will appear as broadband noise to the CDMA receiver except for the unique signal that was created with the same Walsh code. The basic principle behind the use of an 8-bit Walsh orthogonal spreading code to create a distinct signal is shown in this block diagram, which is on the slide now. The spreading of the code increases the number of bits sent in the same time interval as the original digital signal and hence increases overall signal bandwidth. The forward channels in the CDMA system are encoded differently than the reverse channels. The different encoding schemes would be studied in the next coming slides. Additionally, two types of pseudo-random noise codes are used by the IS-95 CDMA systems. These two types of PN code, that is pseudo-noise code sequences, are known as short and long PN codes. The short PN code is the time shifted to identify this particular CDMA base station and to provide time synchronization signals to the subscriber device so that it can become time synchronized with the radio base station. The long pseudo noise code is used to provide data scrambling on the forward traffic channels and for providing a means by which reverse link channels may be distinguished. For an IS-95 CDMA cellular system, a single radio base station may consist of up to 64 separate channel elements that all use the same carrier frequency or portion of the frequency spectrum. Each of the base station's modulated signals effectively becomes a separate channel when the digital signal to be transmitted is encoded with a distinct Walsh code. Several of the Walsh codes are reversed for the use with particular forward channels that serve various logical system functions as it is done. Now moving on further, we will study about the forward logical channel, how it would be. In IS-95 CDMA, forward channels exist between the CDMA base station and the subscriber devices. The first CDMA systems use the same frequency spectrum as the AMPS and NA-TDMA systems. The IS-95 signal occupies a bandwidth of approximately 1.25 MHz, whereas the AMPS and NA-TDMA system standards each specify a signal bandwidth of 30 kHz. Therefore, an IS-95 signal will occupy approximately the same bandwidth as 42 AMPS or NA-TDMA channels. Although the bandwidth required for a CDMA signal is substantial, a cellular service provider is able to overlay an IS-95 CDMA system with enhanced data capabilities onto an earlier generation cellular system. The basic spreading procedure used on the forward CDMA channel is as shown here in this slide. We can see here we have the Walsh code, that is the digital signal to be transmitted over a particular forward channel is spread first exclusive ORing it with a particular Walsh code. We can see here we have the exclusive Walsh code along with the exclusive OR. Then the signal is further scrambled in phase, that is in phase and quadrature phase, that is we can see the I channel pilot and the Q channel pilot lines by two different short PN pseudo spreading codes, that is pseudo noise codes. These short PN spreading codes are not orthogonal codes. However, they have excellent cross correlation and auto correlation properties that make them useful for this application. Additionally, all the Walsh codes are not created equal when it comes to the amount of spectrum spreading they produce. The use of short PN spreading codes assures that each channel is spread sufficiently over the entire bandwidth. The 1.25 MHz channel, the short in phase and quadrature PN spreading codes are generated by two lines feedback shift registers of length 15 with a set polynomial value used to configure the feedback paths of each of the LFSRs. In addition to this, the resulting short PN spreading codes are repeating binary sequences that have approximately equal numbers of zeros and ones and a length of 32,768. The outputs of these in phase and the quadrature phase signals are passed through baseband filters and then applied to an RF quadrature modulator in IC that up-converts the final output signal into the UHF signal frequency bands. This channel element signal linearly combined with other forward channel element signals amplified, and the composite band signal is transmitted over air interface. The short pseudo noise spreading codes provide the CDMA system with the ability to differentiate between different base stations transmitting on the same frequency. The same short PN code sequence is used by CDMA base stations. However, each base station, the PN sequence is offset from the sequences used over other area base stations. Now moving on further, we have the CDMA base station timing offset reuse. Now moving on to the pilot channel, generation of pilot channel signal. The CDMA pilot channel is used to provide a reference signal for all the SDs within a cell. When we look upon this block diagram which is shown in this slide, we have the all zeros Walsh codes is used for the initial signal spreading on a sequence of all zeros, which would result in a sequence of all zeros that are further spread using the short PN spreading sequences, resulting in a sequence of zeros and ones. The in phase and the quadrature signals drive a quadrature modulator. Therefore, the resulting pilot signal is an unmodulated spread spectrum signal. The short PN spreading code is used to identify the base station, and the pilot signal is transmitted at a fixed output power, usually 4 to 6 dB, that is decibel stronger than any other channel. The pilot channel transmitted continuously is used as a phase reference for the coherent demodulation of all other channels. It also serves as a reference for signal strength measurements and other signal power comparisons. Moving on, we have the synchronization channel. The CDMA synchronization channel is used by the system to provide initial synchronization this slide shows the CDMA synchronization channel signal. The generation of the synchronization channel in this case, the Walsh code is used to spread the synchronization channel message. Again, the same short PN spreading code with the same offset is used to further spread the signal. This maintained in the sync message includes the system and network identification codes, identification of paging channel, data rates, the offset value of the short PN spreading codes, and the state of the long PN spreading codes. Like this pilot channel, the synchronization channel has a fixed output power, which we'll be seeing next is a paging channel concept. Coming to the paging channels, the CDMA paging channels serve the same purpose as the paging channel in a GSM cellular system. These channels are used to page the SDs when there is a mobile terminated call and to send control messages to the SDs when call setup is taking place. For IS, we can have a look at the block diagram that is shown in this slide, which that is shared in this slide. For IS-95 CDMA, there can be as many as 7 paging channels in operation at any one time. Walsh code are used for this purpose. The paging channel undergoes an additional scrambling operation using the long pseudo noise spreading code sequence. The long pseudo noise code is generated by using a 42-bit linear feedback shift registers, that is LFSRs, that yields a repeating sequence of length 2 to the power of 42. The paging channel message also goes through a convolutional encoding process, symbol repetition, and block interleaving before being scrambled by a slower version of the long pseudo noise code. So this is about the paging channel. Next comes the power or the traffic control channels. The CDMA forward traffic channels carry the actual user information. This digitally encoded voice or data can be transmitted at several different data rates for IS-95 CDMA. The generation of a forward, in the generation of a forward traffic channel, the rate set to traffic, an additional operation is performed after the symbol repetition block. For a data rate of 14.4 kbps, the output from the symbol repetition block will be 28.8 kbps. The puncher function block selects 4 bits out of every 6 offered and thus reduces the data rate of 19.2 kbps, which is what the block interleaver needs to see. All the CDMA systems, unused Walsh codes may be used to generate forward traffic channels. The traffic channels are further scrambled with both short PN sequence codes and long PN sequence codes before transmissions. The power control information is transmitted to the mobile station within the cell over the channel. This power control information is used to set the output power of the mobile on the reverse link and is multiplexed with the scrambled voice bits at a rate of about 800 bits per second, or 1 bit for every 1.25 millisecond, which is shown in the block. Next, coming to the reverse logical channel, the IS-95A reverse logical channel has that is which is shown here, which is shown in the slide, right? This slide depicts the reverse logical channel. The encoding of digital information on the reverse channel is performed differently than on the forward channel. The data to be transmitted is not initially spread by a Walsh code. Instead, the data is mapped into the Walsh code that are transmitted. Since there are 64 bits of Walsh codes, every 6 bits of a data to be transmitted may be mapped to a particular Walsh code. This technique yields an over 10-fold increase in bandwidth, since 64 bits are now transmitted for every 6 bits of data. However, the system error rate is reduced in the process. The mapping of groups of 6 data bits to a Walsh code is very straightforward, since there exists a one-to-one relationship between the two. Each reverse channel is spread by a long pseudo noise sequence code and scrambled by the short pseudo noise code. The long pseudo noise sequence code is derived from the subscriber device's 32-bit electronic serial number and therefore provides the means by which the user is uniquely identified within the CDMA systems. There are basically two types of reverse CDMA channels. One is the access channels and the reverse traffic or control channels. These logical channels will be, these access channels and the control channels will be discussed in the next coming videos. Thank you. Hope this video is useful to you. It gives an immense which gives an immense knowledge on the CDMA channel concepts. Thank you for watching.